Hai and Assalamualaikum everyone. My name is Nuriza Mustafa, and the topic of journal that need to be discussed is the effect of combustion efficiency on an Otto cycle. I will give a brief introduction about the topic. What is Otto cycle? An Otto cycle is the thermodynamic cycle that describes the functioning of a typical spark ignition piston engine. It is the thermodynamic cycle most commonly found in automobile engines. In other words, we study the Otto cycle to understand what takes place inside the internal combustion engine. There are two types of engine that use the Otto cycle, which is two-stroke and four-stroke engine. The Otto cycle provides the energy for mass transportation and was essential for the modern world. Specifically, the vast automobile seen on the road today use the Otto cycle to convert gasoline into motion. The aim in this study is to know the combustion efficiency influence the performance of an irreversible Otto cycle under condition of varying fuel-air ratio. The irreversibility of Otto cycle comes exclusively from the expansion and compression process. It is assumed that some fraction of the fuel chemical energy cannot be fully released inside the engine because of incomplete combustion. The utilization ratio introduced the concept of combustion efficiency, which is heat addition process at constant volume that described as a function of fuel energy. In order to have a fairly realistic operating condition, it is assumed that the total cycle time and the fuel consumed per cycle are constant. The mathematical model is developed, and the combustion efficiency approach can be lead to a qualitative understanding on how engine loss can be reduced.
Hi everyone, my name is Shafia Hanani, and I will explain on the schematic diagrams. For Otto cycle, there are two diagrams that involve, which PV diagram and TS diagram. In Otto cycle, there is 4 different processes that involve in it. For process number 1, it occurs at state 1 to state 2. For PV diagram, there is an involvement of isentropic process in it, where the volume is decreasing from BDC to TDC due to the compression process. The pressure is increasing from P1 to P2. For TS diagram, the temperature is increasing from T1 to T2, and the value of entropy is the same, which S1 is equal to S2. For process number 3, it occurs at state number 3 to state number 4, where there is an involvement of isentropic process, and the volume is increasing from TDC to BDC. The pressure is decreasing due to the expansion process. As for TS diagram, the value of entropy remains the same due to the isentropic process, which S3 is equal to S4, and the temperature is decreasing from T3 to T4. For process number 4, it occurs at state number 4 to state number 1. For PV diagram, the volume is remain constant at BDC, and the pressure is decreasing from P4 to P1. And for the TS diagram, the temperature is decreasing as well as the entropy value. Thank you.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Rais Hakim bin Rosli. So for today, I will explain about the method of analysis for our research, which is the effect of combustion efficiency on an Otto cycle. So let's proceed. So in this research, we have to do 3 types of analysis, which is the first is the formula of combustion efficiency. Next, the relationship between the combustion efficiency and the air-fuel mass ratio, and also the compression ratio. And lastly is the relationship combustion efficiency and the work output and the fuel combustion efficiency. So for the first, we have to use this formula to gain our value for our data. So for From the data, we can analyze the relationship between the combustion efficiency, the air-fuel mass ratio, and the compression ratio. As we can see, the combustion efficiency is directly proportional to the air-fuel mass ratio. Next, we also can see that the higher the value of combustion efficiency, the lower the value of compression ratio, providing a linear mixture. And lastly, uh, from the data, we can analyze the combustion efficiency and the work output and the fuel combustion efficiency. As we can see, both have same characteristic of curve against the combustion efficiency. So we can say that the increasing maximum cycle temperature rise dominantly the work output with the increasing the combustion efficiency. So we can conclude that the higher the air-fuel ratio significantly improve the general characteristic of the fuel combustion efficiency curve. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Norazi Shairani bin Safi'i and I will talk about the performance calculation of the system in our study journal. This is the TS diagram for an Otto cycle. There will be an actual and ideal in the compression and expansion process which involve between state 1 to 2 and 3 to 4. First and foremost, in order to find the amount of fuel energy needed per cycle, we're going to apply the first equation as shown. Then, by combining the fuel chemical energy factor and the heat input formula, we will obtain the fifth equation that we're going to use later on. For analyzing the compression and expansion process with the presence of irreversibility, the formula to find the isentropic compression efficiency and isentropic expansion efficiency will involve both actual and ideal temperature in state 2 and 4. The ideal temperature can be derived by the means of second law of thermodynamics in equation 9 and 10. By substitute the 6 and 9 equation to the 5th equation, we will obtain the new equation as shown. The 12th equation specifies the amount of heat addition at constant volume process. The heat and work output can be written as stated in equation 13 and 14. Furthermore, the 15th equation is the irreversible thermal efficiency of an Otto cycle. Next, we can use two different formulas in order to find the fuel conversion efficiency. Last but not least, both equation 18 and 19 can be obtained by differentiate the equation 14 by different terms. We will differentiate the work output with respect to the compression ratio for equation 18, while differentiate with respect to combustion efficiency for equation 19. The values from equation 19 can be defined as the upper limit values for the combustion efficiency as it satisfies the cycle feasibility and yield positive values for the compression ratio. That's all from me.
Assalamualaikum and hello. I'm Afif Farhan bin Azhar Rasul and one of the members for the Akatsuki team. My main topic for this journal analysis is suggestion for efficiency improvement. Mostly, internal combustion engines are not efficient at turning fuel burned into usable energy. Average efficiency for most IC engines around only 20%. That is because of the energy loss and incomplete combustion process. From this, I will suggest different ideas to overcome these issues. First of all, my first suggestion is to decrease the compression ratio. From figure 2a, the work curve generally reach their maximum points at a value of compression ratio between 13.5 to 22.5. The results show us that there are certain circumstances where low compression will enhance efficiency. Also, figure 2b shows a nearly linear relationship between the combustion efficiency and compression ratio. However, lower the compression ratio method must be followed up in my next suggestion to meet its demand. Next, my suggestion is to provide the linear mixtures. This suggestion is related to the first one, which will produce better efficiency. Figure 3a shows the combustion efficiency as a near unity value of 0.98 for the linear mixture at 3600 Kelvin. Meanwhile, the combustion efficiency for standard stoichiometric mixture between only 0.5 and 0.8. As for 3b, the highest value for the combustion efficiency can be obtained by reducing the compression ratios and supplying linear mixture.